Hey all, this is Derek, and this is Partial Fractions Continued here, part 2. So in the first video, we looked at the methods. So we had method 1 and method 2. And so method 1, that's the one where I plug the zeros in. That's going to be great if you have zeros. And for me, if I have a zero, I use it. And then method 2 is better if you have few or no zeros. Even if I have just one zero, I still plug it in, and I'll show you an example with that, just because it takes the method 2 piece of it and makes it a lot simpler if I can eliminate even one of the variables. So dependent on how many zeros I have, I'll use one or two, sort of depending on how the problem looks. And there's somewhere I'll use all ones, somewhere I'll use all two, and then there's somewhere I'll use kind of a combination of both methods. The other thing that we have to look at is how to get the right-hand side set up. So back here, when I was doing methods 1 and methods 2, I took this and I rewrote this as a sum of a couple of terms. There's kind of a whole art to this piece, and that is this box. So this is telling us how we're going to set up the right-hand side of our equations. And we're going to look at 4 possible cases. We're going to look at linear factors, and we're going to look at quadratic factors. The quadratic factors are going to be irreducible. So that's to say, if I have something like 1 over x squared minus 4, that would be a reducible quadratic. I could rewrite that as 2 linear terms. So when we're talking about irreducible quadratics, we're talking things like x squared plus 4, or say x squared minus 5x plus 1. There's nothing that multiplies to 1 and adds to be negative 5. So this doesn't factor further, it's irreducible. So that's these. And we're going to have non-repeated and repeated. This stuff, when I do this in class, people just, it's awful. So I'm going to show it with some actual examples. I think that generally goes better rather than this sort of more formal chart. I'm starting with non-repeated linear factors. So right here, and I'm not going to solve these at all, I just want to show the setup for each version so that piece is squared away, and then we can do the really big solves that are coming here in a second. But for getting things set up, this one would be, like I said, a non-repeated, they're different, linear, the x's are to the first factors. And so this one, we would just set up something a over x plus 1 plus b over x plus 2. And we usually just use A, B, C, D, E, and just count out letters for as many as we need. And it's customary to use capitals, so that's just sort of the custom. So this would be my setup for my right-hand side. So that's what this non-repeated linear factor thing over here is saying, is you just set up one of those for as many as you have. So if I had an x here on the end, I would have c over x. So each term just gets its own letter. When I have a repeated linear factor, so this is x plus 1 squared, I would have a over x plus 1 plus b over x plus 1 squared. And then say that was cubed instead, then I would have c over x plus 1 cubed. So I just have to set up one term for each possible outcome on the denominator. Say it was a cube, just because I actually like that example better. I could have an x to the first term, because that could have been involved in here. I have to have at least an x cubed term somewhere, because I had at least 3 of these. Maybe I have 2, maybe I have a squared term, maybe I don't, maybe I have a linear term, maybe I don't. LCD for those would still be x cubed. LCD for this would still be, x plus 1 cubed. And so I just have to allow for all the possibilities. It may be that some of these come up, well, either A or B could come up 0, and we didn't need that term, but we have to allow for all the possibilities. So this next one, this is a non-repeated irreducible quadratic. So they are different, they are quadratic because they are squared inside. Notice it's not like the square on the outside, it's the inside. So linear, linear, quadratic, quadratic. It's not the square outside that counts, it's the one inside that does. And for quadratic, we set it up under a linear term. So ax plus b over x squared plus 1 plus cx plus d over x squared plus 2. So notice we're just setting up proper fractions. So this is like ax to the 0, so it's always 1 degree less than the denominator. If we were working with cubes, we would have a ax squared plus bx plus c up in the numerator. And then this one is the repeated irreducible quadratic. So this is going to act just like this, where we just do ax plus b over one factor of it, so I don't really need that parenthesis, and then cx plus d over x squared plus 1 squared. So that's how we set up each of those individually. And then what you'll see in the problems is that we're going to have combinations of these kind of 4 conditions, and we'll set up terms accordingly. Okay, so this first one we got to check and see if this factors. If there's 2 things multiplied to be -3 and add to be -2, which there are, that means we have to factor this, and that means we're going to have linear terms. So this would be x plus 1 and x minus 3. We'd multiply to be -3 and then add to be -2. So my right hand side is going to be a over x plus 1 plus b over x minus 3. And this one, I have 2 unknowns, I have 2 zeros, so I'm set. I just got to toss the zeros in. So I'm going to multiply both sides by the LCD, and the LCD is always just what's right here. And so on this side, it knocks out everything, and I'm left with 2x minus 1. On this side, what it's gonna do is it's gonna cancel itself and leave the what's left. So here the a plus 1s, if you think of this, or x plus 1s, would cancel, leaving the a and the x plus 3. Sorry, minus 3. And then here the minus 3s would cancel, leaving the b and the x plus 1. So whatever here goes away, and then whatever's left is what's with the variable. So it'll be b and x plus 1. And then this one, since I have zeros, I don't want to distribute because that will actually make it harder. So I'll just let x equal, my first zero would be -1. So 2 -1 minus 1, a -1 minus 3. Again, when I put -1 plus 1 right there, that makes 0b, so that drops out. So this would be -3, yeah, -2 minus 1 makes -3. And then this would be -4a. And so dividing that over, a equals 3/4. And it can happen that they come out to fractions. And then our other zero was 3, so let's toss that in. So this would be 2, and then times 3 minus 1. This time the a term drops out because 3 minus 2 would be 0a. And we're left with b, 3 plus 1. So this is 6 minus 1 would be 5 equals 4b. Divide that over, and b equals 5/4. So then the way that we write our answer, and I've seen it both ways, where they just put the 3/4 up here and the 5/4 up here. When I was looking at the answer on this, it had it like this. So I'll show this version, but both of those would be correct. But that's how the computer had it formatted, with the denominators just down in the denominator of the fraction. Okay, so for this one we have 2x is a linear term, so it's going to get an a and 2x, and then x plus 1 squared, so that is a repeated linear, so that's going to get a b over x plus 1 plus a c over x plus 1 squared. And when I do this in class, I'll get the question, isn't this quadratic? And the answer is yes, but it is a repeated linear quadratic, because if you have repeated linear terms, that will be quadratic or possibly cubic or whatever. But the important thing is inside it's x to the first. So that factor is linear, even though this denominator is quadratic. So we're talking about the factor. And then the number of times it repeats, that tells us how many of those we need. So this is my LCD, so I'm just going to write LCD to save myself a little bit of writing in this section, because it's a horrible section of writing. So all this cancels, and over here I'm left with 3x squared minus 4x minus 2. The 2 x's would cancel, so it's going to leave me x plus 1 squared times that a. And you can certainly, write it out. If you're having a hard time seeing that canceling, write that stuff out, and you'll see how it cancels with each of those terms. I don't have a ton of room, so that's where I'm kind of skipping a little bit of the writing there. And then here we're going to have plus b, it's going to knock out one of these x plus 1s, so I'd be left with a times 2x and an x plus 1, because one of them got canceled. And then c times 2x. So that's what we got. We have two zeros. We could have x equals 0 right here, and x equals -1. So let's use those, and that's going to get us two of our three variables. And then once we have two of them, it's not the hardest thing to get the third. So we'll let x equal 0 because that's easy. So when x is 0, that's all gone. I have -2. 0 times all that who cares is gone. 0 times who cares is gone. So just that a term survives. So that will be 0 plus 1 squared, which is 1. So pretty much a ended up -2 without me doing too much work there. And then next up, we're going to let x equal, let x equal 0. And now I'm going to let x equal -1. And that will have to do a little bit slightly more work. So 3 times -1 squared minus 4 times -1 minus 2, -1 plus 1. So a term drops out, -1 plus 1, b term drops out. So this is going to let me get c. And I don't need that parenthesis there, sorry. So c times 2 times -1. So that is 3 plus 4 minus 2 equals -2c. And that is 7 minus 2 is 5 equals -2c. And then dividing over, looks like c equals -5 halves. So now we know a and b. And so what I'm going to do is now we know a and c. And so what I'm going to do is plug these back into this one. And then that's going to get me an equation where I just have b's and x's, and I can make up x. So I haven't used x equals 1 yet, and that's a pretty easy number. So I'm going to let x equal 1, plug it into this equation. I know a is -2, I know c is -5 halves, and then that's going to let me get b right there. So we're going to let x equal 1, just because we can pick whatever value of x we like. We picked the zeros because they're helpful, but we could have picked 3 values, set everything equal, and then the system's version of this as well. So we'll let x equal 1 with a as -2 and c as -5 halves. So coming up here, I'm going to have 3, 1 squared minus 4 times 1 minus 2. A was -2, 1 plus 1 squared. B is what we are trying to work out. So b, and then that is 2 times 1 is 2, and then 1 plus 1 would be another 2 right there. Plus c is -5 halves times 2 times x is 1, so times 2. So this mess, 1 squared is 1, and so that's a 3 minus 4 minus 2. 1 and 1 would be 2 squared. 2 squared would make 4, and then 4 times 2 should be 8. And negative because that sign, plus 4b. Those 2's cancel, and minus 5. So then this would be 3 minus 6, so that is -3. This is minus 8 minus 5, so that is minus 13 plus 4b. Add the 13 over, and that would be 10 equals 4b. And so then dividing the 4 on both sides, it looks like b equals 10 over 4, so that would be 5 halves. So then finally going back to this original equation up here, we would have a was -2. So notice when I put in -2 for this a back here, I'm going to have -2 over -2, and those are going to cancel. So I'm going to write that as, let me just show it, -2 over -2x. So I'm canceling those, and I'm going to write this as negative 1 over x for that first term, just so I don't have to rewrite all of it a couple of times. B, that's going to be plus 5 over 2x plus 1. So there's my B was 5 halves. And then that C was negative 5 halves, so we'll make that minus 5 halves x plus 1 quantity squared.